In this video class, I'll be looking at velocity time graph, still under the topic graphs of motion or simply motion graphs. In the previous videos, I explained the distance time graph and the displacement time graph and how to find the slope, and that the slope of the distance time graph represents speed. Now, for velocity time graph, we have the graph of increasing velocity plotted or drawn against the vertical axis and the time represented by the horizontal axis. So this is a case of constant velocity. You can see here that the graph is a straight line parallel to the time axis, meaning that the velocity does not depend on time. After 1 second, let's say around here, if you trace it to the graph, it's still at 10, the speed is 10. After 2 seconds, velocity remains 10. After 3 seconds or 4 seconds, velocity remains 10. And after 5 seconds, it's 10. Which means for 5 seconds, this body has been moving with a constant velocity of 5 seconds. Now, if I want to represent this constant velocity on a displacement time graph, I'm shifting to a different domain. The velocity time graph is one domain. The displacement time graph is another domain. How do I draw this graph? I guess you should be able to do that because that is what we did in a previous class, drawing displacement time graph. So when you have a constant velocity of 10 meters per second, the velocity is kept constant for 5 seconds. Now, representing that on the displacement time graph is a straight line. Because that I'm drawing sketches here, I'm not using my graph book. I guess by the time you are done with me learning how to do all these things, you'll be able to, on your own, draw these graphs on a graph book. Okay, so this is a picture. This same information, constant velocity, represented on a displacement time graph. And if I want to represent it completely, which means after 5 seconds, let me place my 5 here. After 5 seconds here, the body will have covered a distance of 50 meters. How did I get that? 50 meters, because distance or displacement is speed or velocity times time. So by the time I multiply 5 by 10, that is 50 after 5 seconds. That's covered a total displacement of 50 meters from the starting point. And what you need to note about a velocity time graph, that number one, the slope of this graph represents acceleration. The slope of a velocity time graph stands for acceleration. So that's the first thing. And number two, the area under the graph, the area is bounded by the graph line, the ordinates, and the time axis is total represent the total distance covered. So important points to note. So you need to write this down. Total distance covered by the body is the area under the graph. And this 50 meters, I can also get, if I come back to my velocity time graph, I'll just take a line. This is my ordinates. This line is called the ordinate. So the area of this rectangle represents the total distance covered. And that area is length times breadth. The length is 10, the breadth is 5. So 10 times 5 gives me 50 meters, not 50 meters squared though, because we're just saying area represents the displacement or total distance traveled by the body, not actually area in meters squared. So this is how we translate. We go between two domains. The same information represented on two different graphs. Velocity time graph, constant velocity represent that. And then on a displacement time graph, this is what it is. Then on this acceleration time graph, a graph of constant velocity means zero acceleration. If I'm to draw that here, I'll just draw it along the parallel or along the time axis. Here, acceleration is zero because when the body's velocity is constant, meaning it does not change, the body has zero acceleration as long as the body is moving in a straight line. Okay, so now let's look at the second graph. We want to draw the graph of constant acceleration. Number one, on a velocity time graph. Now let's say from this table you are given the variation of the distance, the velocity of a body against the time taken. At 0 second, the speed or velocity is 0. After 1 second, the velocity is 10. After 2 seconds, body is moving at a velocity of 20 meters per second. After 3 seconds, even the velocity of 30 meters per second, so on. If I translate this graphically or to the graph of velocity versus time, I have these plots. So by the time I join this plot with a straight line or with a line, it gives me a straight line graph starting from the origin. Now, the straight line graph, of course, I said earlier that the slope represents acceleration, and the straight line graph has a constant acceleration. Constant acceleration. A straight line graph has a constant slope, meaning that it has a constant acceleration. And you can see the way the speed of this body increases from 0 to 50 meters per second. I would advise you not to, if you are maybe learning to drive a car and you jump into your daddy's car, don't go and increase your speed to 50, because then you'll be inviting death to yourself. This is just an example. Don't increase your speed to 50. So you can see that if the speed continues, if the body maintains a constant acceleration, the speed increases continuously until it gets to 50 meters per second after 5 seconds. How do we find this acceleration, which is the rate of increase of the velocity of speed of this body? Of course, you can choose any 2 points again. This point, I can choose this as my point 2. I take this point as my point 1. And the next thing is to draw my slope triangle. I draw my slope triangle like this. This might change in velocity. This might change in time. So my change in velocity or change in time, my v, that gives me v2 minus v1 over t2 minus t1. My v2 traced to the velocity as it gives me 40 minus, come to point 1. My t1 is 10 over my t2, that is 4 seconds, minus my t1, that is 1. That gives me 30 over 3. That gives me 10 meters per second squared. Of course, that is acceleration. That's why I put the unit meter per second squared there. So you can see that the slope of a velocity time graph represents acceleration. And here the slope is constant. It means that this is a graph of uniform. This is a graph of uniform acceleration. This is the graph of uniform acceleration. Okay. Now the distance covered, let's say in 5 seconds. You have to calculate the distance covered in 5 seconds. What distance did the body cover in 5 seconds? We have to come back to the graph. And then in my graph, I have to take this time up, take a line from this time up, maybe a broken line, to meet the graph somewhere here. So in 5 seconds, we expect that the speed, if the acceleration is maintained, would be 50. Or the distance covered in 4 seconds. I want to use 4, since that one is clearly on the graph space. 4 seconds becomes the area bounded by these lines, the graph, the ordinates, and the time axis. And this distance S is given by the area of the triangle. Area of triangle, because that shape is the triangle, the shaded part here. This line, the time axis, and the graph line, which gives me half base times height, half base multiplied by the height of the body, of the shape rather. That gives me distance traveled is half times the base from here to here, that is 4 seconds, which is the time. The height are measured along the velocity axis, that is corresponding to 40. That gives me 80 meters. So the distance traveled in 4 seconds by the body is 80 meters. Now, before we close, let's look at this particular graph. You are given this graph of a body that starts from rest, and then they may ask you to describe the motion of this body. You start from this point O, and then after 5 seconds, he attains a speed of 30 meters per second. And then between 5 and 8 seconds, the speed stays the same. No more increase in speed, no more decrease in speed. It remains constant for 3 seconds. So sometimes they can give you a graph like this, a picture like this, and say describe the graph of the motion of the body. Or sorry, describe the motion of the body You see, the body starts from rest and moves with a constant acceleration. Because on a velocity time graph, a straight line graph like this of this nature with positive inclination, angle of inclination, is a graph of uniform acceleration. So you can start by saying the body starts from rest and accelerates uniformly and moves with a constant acceleration of maybe quickly you can find the slope using this point and this point to calculate the slope. Use my slope triangle. This is my change in speed, which is 30, over change in time, which is 5. So it started from rest and moved with a constant acceleration of 6 meters per second and attained a maximum speed or velocity of 30 meters per second in 5 seconds. That's the description. And then between time t equals 5 to time t equals 8 seconds, the velocity of the body stays the same. That is, the body moves with a constant velocity of 30 meters per second, and within this time interval, its acceleration is zero. Because when velocity is constant, the acceleration of the body is taken as zero. So quickly we can find the total distance covered. If we have to determine number one, the total distance covered by the body, and that will be given by area of this shape. By the time I place a line here to extend this to my 8-second mark, I have a trapezium. The entire shape is a trapezium or consists of a triangle and a rectangle. And the formula for calculating a trapezium is half the sum of the two sides that are parallel times the height of the figure. Now I can identify my sides A and B. A and B are the parallel sides. This A, from here to here, I call that A, this line. And my B is from the origin to here, where I have 8 seconds. I call that my B. So that the distance covered, my A is 8 minus 5, which is 3, plus my B is 8, times the height. The height is along the velocity axis, which is 30. So that gives me half times 11 times 30. So that gives me a total distance of 165 meters. So that's the distance covered, the total distance covered by the body in the course of moving in a time of 8 seconds. Okay, so next video we shall take more question on this.